In the last video, we talked about motion queuing as a two-step process. And these are the two steps, and we're going to take a look at that first step, the filtering, that turns vehicle motion into platform motion. Well, if I just showed you this, you would hardly be able to do anything with it. You could probably do a lot of learning and then gruntingly, unwillingly follow some instructions and come up with a solution. But what I want you to think when you think of this is the solution to a problem that you probably are unaware of. So before I just show you the solution, I would like to introduce you to the problem. I'm going to show you some wrong ways of doing it so that when eventually I'm going to show you this, you will recognize this as the solution to your motion queuing problem. So come along for the ride. We're going to make a couple of mistakes, but these mistakes are going to highlight a certain need that you have, and then eventually you will realize when I show you the filters or the Excel graphs, you will then realize that, oh yeah, that is the solution to what I actually need. So come along and let's see how we can do motion queuing in the wrong way first. So if we were using the data from the vehicle directly, like using the longitudinal acceleration to drive the surge axis of the platform, it would essentially be doing this, using the acceleration longitudinal to drive the platform, but without any filters in between. So for now, just follow along and do it without any filters, and you're going to see where the problem lies. So just assume there's a car. And the car is stationary, the light is red, and all of a sudden that light turns green and the car starts accelerating. You see it's accelerating, and here's what we're going to look at, the position of the car, the longitudinal acceleration, the longitudinal velocity of that car. So we're standing still right here, no movement, the position is 0, and at a certain point here the car starts changing its position, and because it's accelerating, that is basically the parabola shape. But the velocity of the car is 0 all the way here, and in the point the car starts accelerating, the velocity starts to increase, but it's a linear increase. Now the acceleration of the car, the longitudinal acceleration of the car is 0 all the way to that point, and then snap, there is acceleration. It goes from no acceleration to there is some acceleration in an instant, and that acceleration stays constant. So keep in mind, the data that we are exporting is the longitudinal acceleration. You see, longitudinal acceleration of the vehicle, which is this graph. So nothing coming in, and then all of a sudden there is some number that represents the longitudinal acceleration. So if we used that data to drive the motion platform, here's what it looks like. And you can look at it at a screen, but it's more important for you to try to imagine it. What would it look like if your platform was driven by that data in the surge axis? That means there's no surge on your platform here, and then all of a sudden, in an instant, the platform would jump forward, like by whatever amount you set it up for, and then there is surge present, and then it would never change. If you use that data directly to drive your surge axis, your platform would make an infinitely fast jolt forward. There would be an infinite acceleration. There's infinite velocity in this very moment. That's why this line is vertical. So you can't use that data directly. I'm going to show you what it would look like. So here's the platform. This is a representation of the platform in my software. These green dots indicate the forward direction, the green arrow, I mean, you're looking in this direction. So let's look at it from the side and see what it would look like if you were to use that data, the longitudinal acceleration, directly to just drive the platform. Here's what would happen. So first of all, the platform would be in the 0 position, just like it's here on the picture, and then boom, your platform would snap forward. It would just move forward instantly. That means there would be infinite velocity and infinite acceleration. And I hope it's not hard for you to see that, first of all, this can never be truly achieved. And second of all, that's not what you want. Remember, what you're trying to mimic is this kind of position change. This is how the car moves along the road. And there's curvature here. And there's actually, this looks like a parabola. So you want to mimic this motion, but all you have is this signal. So let me show you in a different way. You want this curvature here to be present the moment the acceleration pops up. But what you actually want is you want that curvature to be present right here, but you don't want the rig to go off into infinity. So let's see if we can improve on this. Maybe what you want to prefer is a curve that looks like this. So as soon as acceleration pops up, remember this is the data, this is all we have. And this is what we need. We need something that gradually accelerates and then eventually comes to a stop and won't break the limits of your rig. Even better would be if the platform would move forward, come to a gentle stop, and then just be gradually brought back to its center, because at some point your car will have another acceleration happening to it. So what you want is a curve that initially follows that parabola and then eventually diverts from it gently, and then very gently is being brought back to the 0 position. So let's see what we can do to our curves in Excel to actually get this shape. So in a nutshell, we have to find a way to turn this signal, this square signal, I'm tempted to say this step input, we need to find a way to turn this into this smooth curve that pops up and then gradually dies down, or maybe even pops up and then stays where it is. Like, both cases are present in motion queuing, but we need to find a way to turn this into this, and we're going to use Excel and some filters and some combinations of filters to achieve this. So this is what our Excel sheet looks like, and please be aware that the blue input signal is our acceleration signal that we just saw when the car was accelerating. It's 0 all the way, then jumps up to some acceleration, doesn't matter what it is, it's just represented as 1 here. And then we're going to use the output signal that we're creating to drive the platform. So we have an input signal that makes a step, we need an output signal that has a smooth transition. So we're using the first order low pass, the green line, to connect these dots, but there's still a corner. And we're using the second order low pass to create tangency. So be aware that if we're using this as an output signal, then the value that that signal has is the position of your platform. And if that makes a jump, then it's going to be pretty uncomfortable on your platform. The gradient represents the velocity of your platform, and the acceleration is represented by the curvature. So if we use a first order low pass, we have immediate velocity, but there's a smooth gradient at least, and the second order low pass will turn it into tangency. So the second order low pass will create curvature right here immediately on that yellow line. So if we use a second order low pass, we can turn a signal that makes a jump from no acceleration to some acceleration, and we can turn it into a signal that represents no curvature into right here, in an instant, there is some curvature. And remember, curvature represents acceleration if we're using that to drive your search platform. So you might be tempted to use the second order low pass filter. And if you did that, then your rig would essentially do nothing up until here, and then when acceleration shows up in that car and the data, your rig will move along this yellow graph. It'll have the initial part is kind of like a parabola, so it moves exactly how you expect it for the first well, probably half a second, but then eventually die down, it'll slow down and then stay at that value up here, which is a good first step. Remember, when you're sitting on the platform, it starts to move forward. This curvature is pretty noticeable. It's above your threshold of perception, but this long curvature back here is below your threshold, should be below your threshold of perception, and then the platform is all the way in the front. But what you would rather have is like make this line go back to 0, and that's what we're going to do with the high pass filter. So up until now we have only been talking about low pass filters, and low pass filters, well, they smoothen stuff out and they create these nice curves, but we want to bring it back to the 0 position, and that's why we have to look into that Excel sheet once more. Well, here we are in Excel, and I certainly hope that you have been following along, and this is what we've been doing with low pass filters. But what we want to take a look at now is a high pass filter. Now, the high pass filter is essentially just the opposite of a low pass filter. So what we've been doing here is essentially just using the input, which is the step input, makes a step at time equals 1, and we're creating one low pass filter output. It's that green line. That's what you've been used to. It's this green line, and it smoothly adopts that new value. But what we want instead is the difference between the green line and that signal. So our output, the high pass output, is just the difference between the input signal and that green line, which essentially does nothing but just flip this green line inverted. And that's how this yellow line comes to be. So the first thing we're doing is we're applying a high pass filter. We're creating a low pass filter, subtracting it from the original signal. What we get is a high pass filtered signal, and it's this yellow line. The input signal makes a step. The high pass filter, it just goes with it and then gradually dies down to 0. So instead of using a step input, the first thing we're doing is sending it through a high pass filter. So we have a step input. The step is represented in that signal right here, but then it gradually dies down. So what we have now is that yellow line. And let's put this through our second order low pass filter, and you can see here what it looks like. So if we add one more low pass filter, we get this bright orange line here, and if we add another low pass filter, we get the dark orange line, which is this one right here. And now that's exactly what we need. Remember, the input signal makes a step, there is acceleration, we want the platform to immediately have curvature, that we want the graph to have curvature. That means the platform has acceleration. It'll move the platform forward, but only like it'll follow this parabola shape right here in this very spot, but it'll then diverge from that parabola shape, and with a very large radius. Remember, this is a tight radius, so it's above your threshold of perception. This is a very large radius, which is hopefully below your threshold of perception, and will return the platform back to 0. As an overview, the first thing you do is your high pass filter signal, then you add 2 low pass filters. The high pass filtered signal creates this spike and makes sure the signal dies down to 0. The low pass filter, well, the first one creates this corner, the second one creates this tangency right here. So that's essentially what we're doing in the surge axis. When there is an acceleration, we want the platform to move forward and then gradually come back. And as there is acceleration showing up immediately, there is curvature showing up immediately. So when we use that to drive our platform, we get exactly what we want. I can show you the same thing in this diagram. We're using the longitudinal acceleration, sending it through a high pass, then 2 low pass filters, then a gain that will, well, either blow up or reduce the signal so that it fits within your operating space, and then we're using it to drive the surge degree of freedom. I might as well show you in this diagram. It's the same thing. You take the vehicle accelerations. In this case, they do scaling first, which is essentially the gain. Transformation, don't need to worry about that, but you're sending it through a high pass filter and then a double integration. And this is probably the point where some of you are scratching your heads. Didn't I just tell you that we're using a high pass and a second order low pass? Now what they're doing is a high pass and then a double integration. So in maybe one of the future videos I can explain to you why a low pass filter is essentially the same thing as an integration. So a double low pass is a double integration. But that's details essentially if you really want to dive deeply into it. What I can show you is a couple of different ways to turn a longitudinal acceleration into the surge degree of freedom, high pass, second order low pass, which is essentially a double integration. And that double integration, I'm going to show you something else, something that's also very interesting, and maybe this one here. So we're using the acceleration, but we're using it to drive the surge platform, which is essentially a position. So to get from position down to acceleration, we have to do differentiation. So we take the rate of change over time, we get the velocity, we get the rate of change of the velocity to acceleration. If we want to go back the other direction, if we're going to go from an acceleration to a position, we have to go 2 steps up, well, 2 stories up in that building, so to speak, which is an integration. And going from acceleration to position, that's the reason why they're using a double integration here. And in practicality, integration's hard to do. In reality, a low pass filter much easier to implement. So instead of using these double integrations, we're using a double low pass filter, which is mathematically super, like really dirt cheap to implement. Well, yeah, that being said, probably on a side note, I should add that sometimes in these diagrams, filters actually have the purpose of a filter, and sometimes they have the purpose of being an integrator. Like for example, up here, the high pass, they are just there to make the signal return to 0. We're not really interested in the high frequencies. We're just interested in the property of bringing the signal back to 0 over time. This is a low pass first order, actually a single integration. Here's a low pass second order, actually a double integration. Well, in this case, the low pass third order to drive the longitudinal acceleration into a pitch, that's not an integration. That is a low pass filter that actually has the purpose of filtering low frequencies. So, and that is to keep the rotation rates below your threshold of perception. And in this diagram, I can show you it's that crosswise processing chain. You have a low pass filter, tilt coordination, and then they use a rate limiter. Well, instead of using a rate limiter, which is technically not quite correct, you might as well just use a low pass third order, which has essentially the same result. It'll not just limit the rate, it will also limit the angular acceleration in that degree of freedom. Yeah, so that was pretty much about it. I know there's a lot in this video. Take your time, just be aware that these low pass filters are essentially integrators. They are also double integrations. The third order is an actual low pass filter that is implemented to conceal the rotation from your perception, to push it below your threshold of perception. Yeah, in one of the next videos we can go through some of these other lines, how we can turn an angular rate around the longitudinal axis into your roll degree of freedom and why we're using these here. But essentially it's always the same thing. So just keep looking at that diagram, see what you can do, how you can play around with it, and most of all, yeah, enjoy it.